Well, in the previous lecture, we have discussed most of the physical properties related to the group 1 of S block. Now, in this lecture, I will start some of the chemical properties, and first I will discuss the general reactions for all, and after that I will take up some of the important compounds. So first I am taking reaction with water. Reaction with water. So see, all the elements of this group, they reacts with water. All reacts with water, reacts with water, and normal water, cold water, not heating is not required, reacts with water and produces metal hydroxide, metal hydroxide and hydrogen gas, right? So all reacts with water, and they produces what, uh, I mean metal hydroxide. Corresponding metal hydroxide means if lithium reacts, then the lithium hydroxide, sodium reacts, then sodium hydroxide, right? Like that. So, and the reactivity increases down the group. The reactivity with water increases, the reaction becomes violent on decreasing the group, right? So, the reaction becomes reaction with water becomes violent, becomes violent down the group, down down the group. Means lithium reacts gently, sodium more vigorously, potassium even more vigorously, right? So this, and all of you know that hydrogen, I mean potassium and sodium, they reacts very violently with water, and in all cases you have similar type of product. So M plus H2O, this will give you MOH plus hydrogen, right? Hydrogen gas. And M is equal to lithium, sodium, potassium, rubidium, cesium. Okay, right? Now see their E naught value, standard electrode potential here, that will also we can use to predict the reducing nature of these metals. So if you can see, so E naught for Li plus oblique Li, this is minus 3.05, minus 3.05. E naught of Na plus oblique Na, this is minus 2.71. E naught of K plus oblique K, all these are the reduction potential, standard reduction potential, minus 2.93. E naught of Rb plus oblique Rb, this is minus 2.92, 2.92, and E naught of cesium plus oblique cesium, this is minus 2.92, 2.92, right? So all of you are knowing that these are the reduction potential. So if you want to arrange them in the reducing nature or reducing power, so lithium is the best reducing agent here, right? So how to we can report the reducing power? See, reducing nature is directly proportional to E naught oxidation algebraically, means with sign. Basically, E naught oxidation with sign you have to consider, with sign. You have to consider E naught value with sign. So this is reduction, this is reduction, this is reduction, this is reduction, all are reduction. So oxidation potential, you just change the couple. So this is plus sign. When you change the couple, sign will change. So basically you have to see here plus, 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 plus to decide the reducing nature. Because Li plus cannot be reducing, right? Li plus cannot be reducing. You have to find out Li, right? So for reverse couple, you have to change the sign, because you know E naught oxidation and E naught reduction for any couple is same. The magnitude is same, but the sign is opposite. So reduction is minus, so oxidation is plus. So plus, plus, plus. So highest value is for lithium. So the best reducing agent is the lithium. And after that 2.93, I think this is potassium. After that you will have this 2.92 rubidium, cesium, rubidium, and then sodium, right? So this is the reducing nature, order of reducing nature. Order of reducing nature in aqueous medium. In aqueous medium. So in aqueous medium you have lithium is the best reducing agent, but in gaseous phase you have cesium is the best reducing agent. So this is the application of E naught value. By using this E naught value, you can decide which one is the better reducing agent. Hopefully it is clear to all of you, right? Now the next I will take up the reaction with air. The reaction with air. Reaction with air. So see, all the elements they are very reactive, and they becomes tarnish in air. Sodium, potassium, rubidium, cesium forms oxide or peroxide or superoxide, different kinds of oxides we can say of various type, but lithium forms oxide as well as nitride. So see, if you take lithium, so lithium with air, this will form Li2O and Li3N, right? Oxide and nitrite. And except lithium, if you react, so various kinds of oxide, right? Superoxide, various kinds of compounds we can say, various kinds of binary compounds of oxygen, various kinds of binary compounds of oxygen, right? For example, oxide, you may get oxide, you may get peroxide, and you may get superoxide as well. Superoxide, right? So I will discuss in the detail when I will talk the reaction with oxygen. and here M is equal to NaK, right? Rb and Cs all have ability to form various kinds of binary compounds like oxide, superoxide, and peroxide. Okay. Now the third one is the reaction with oxygen. Reaction with O2. So when these metals, all they react with oxygen, but lithium, when lithium reacts with oxygen, it forms main compound in the direct combination. I am talking about a direct combination. So lithium, if directly combines with oxygen, then it will form lithium oxide, Li2O, right? Li2O. Very little peroxide, means main compound is oxide, lithium oxide. Main compound is this. What is difference between oxide? See, O2 minus is called oxide, O22 minus is called peroxide, and O2 single minus is called superoxide. So if you analyze the formula of this, so you will have this here oxide. So this is the main compound, right? If you react sodium with the oxygen, so this will give you the peroxide Na2O2. This is the main compound. Na2O2 is the main compound. Main compound means peroxide. We will have peroxide, it is the main compound, not normal oxide or superoxide, right? So this is the major compound. Although some oxide is there, very little oxide is there, and very little superoxide. But if you take metal plus oxygen, so you will have this MO2, right? Is the main compound when the metal is potassium, rubidium, and cesium. So this is very important reaction. Many times students are confused here that lithium, this form mainly oxide, very little superoxide or peroxide. Sodium mainly forms peroxide, this is peroxide, this is a normal oxide, and this is superoxide, right? So this is the variation in the products when metals of first group reacts with oxygen, right? So you can see all these metal, they can form normal oxide, right? And but normal oxide you will get only through indirect reaction, means you cannot get direct sodium oxide by direct reaction of sodium with oxygen. So this is the important point here. Okay. So we can say that oxides can be prepared, oxides of all these metals can be prepared, but that is by heating of what, peroxide or superoxides, right? So you can write here that all superoxides and peroxides, here we can put a note, all superoxides and peroxides on heating produces normal oxide, right? For example, if you take Na2O2 and if you heat this, right, so you will have Na2O plus O2, right, half O2 gas. So this is sodium peroxide and this is sodium oxide. So peroxides on heating produces what? Oxygen and normal oxide. Similarly, if you take potassium superoxide KO2, so KO2, that is also on heating produces K2O plus O2, right? K2O plus O2, 2KO2. 3 by 2O2 and half, right? So this is sodium peroxide and this is potassium superoxide. So all superoxides and peroxides on heating produces what? Normal oxide. So normal oxide you can prepare, but indirectly, but you cannot prepare normal oxide directly reaction with oxygen, right? So now see peroxides, if you see the structure of peroxide, so peroxide O single bond O negative negative. So these peroxides are diamagnetic because all the electrons are paired, magnetic, and they are good oxidizing agent. Oxidizing agent, right? But if you take superoxides, so superoxides O2 single minus, this is paramagnetic, and also oxidizing agent. They are also oxidizing agent. But usually they are colored, right? And peroxides normally, except few, most of the peroxides are colorless, right? So see this, if you compare the oxidizing nature of peroxide, superoxide, so obviously superoxides are better oxidizing agent. So superoxides are better oxidizing agent. Superoxide, then peroxide, right? If you compare between superoxide, peroxide, and even oxide, or I mean oxygen. Why superoxides? So we can demonstrate this when the superoxides like KO2 reacts with water. So this will produces the KOH, H2O2 and O2, means hydrogen peroxide and oxygen. So superoxide on reaction with water produces both, means this superoxide oxidizes this water into H2O2 and oxygen. So even, right? So this is the oxidizing order of oxidizing nature, order of oxidizing nature, right? So through this reaction, you can demonstrate that superoxides, these are the superoxides. Superoxides are better oxidizing agent than peroxide and oxygen, right? Now see superoxides like NaO2, very little superoxides formed by this, but this is yellow, and KO2 is orange, KO2 is orange, right? KO2 is orange, and RbO2 is brown, and CSO2 is again orange. So you can say that superoxides, they have color ranges between orange to yellow to orange to brown, right? So, and one more important application of superoxides is that these superoxides like KO2, when this reacts with carbon dioxide, this will give K2CO3 and oxygen. So this KO2, you can say, can act as an absorbent, and absorbent for carbon dioxide and production of oxygen. So this property means it absorbs the carbon dioxide and produces oxygen. This property of these superoxides make them a good chemical for basically for space capsules, in the submarines, or in the place where there is a deficiency of oxygen, right? So in the mask, if you have taken KO2, so this with the reaction with carbon dioxide means what air after breathing you are exhaling, that carbon dioxide reacts with carbon dioxide this and produces oxygen, and oxygen you can use, and K2CO3 is not a harmful chemical, right? So this reaction or this property means absorption oblique reaction with carbon dioxide and production of oxygen gas makes superoxides suitable chemical for space capsules or space aircrafts in the submarines, right? And breathing mask, etc. So this, superoxides are very good, agent for this use of the superoxide is for the absorption of carbon dioxide and release of oxygen where there is a scarcity of oxygen. So this is a little bit about superoxides, and now see peroxides. See, you can consider peroxides as a di-basic, have two replaceable hydrogen. So if you take, NaOH plus H2O2, so this will give you what? Na2O2 plus H2O. So we can say that this sodium peroxide is basically a salt of H2O2 and NaOH. So what is the N factor of H2O2 here? The N factor for H2O2 is here 2 and N factor for NaOH is 1. So basicity of H2O2 is here 2, right? So means this H2O2 is sufficiently acidic. So I will discuss detail about H2O2 in the preparation and properties, right? So this is all about peroxides and superoxides, and all of you are knowing that peroxides are also a very good oxidizing agent, right? So they can use as a bleaching agent as well, but we will discuss H2O2 separately. Now see, the next is reaction with nitrogen, right? Reaction with nitrogen. Reaction with nitrogen or dinitrogen. So you know, only lithium reacts with this in the group. Only lithium reacts with dinitrogen directly. Lithium plus dinitrogen, nitrogen, and if you heat this, you will have Li3N, lithium nitrite, right? And lithium nitrite, on heating, this will give nitrogen. So lithium nitrite, it is ionic compound, and it is a ruby red color. Ruby red in color, and this on heating, again the reverse the reaction, right? So if you heat strongly this, right, so you will have Li plus N2 gas. So you can prepare nitrogen gas by this. And second reaction is also very important, that if we take Li3N plus H2O, so you will have lithium hydroxide plus ammonia. So this is an acid-base reaction, basically. Acid-base reaction. So this is very important reaction, that nitrites, all nitrites on reaction with water produces ammonia, right? So this is all about reaction with nitrogen. Okay. Now see, hydroxides we have already seen. Yes. Yes. Metal hydroxides, and you know, these metal hydroxides, the solubility of these metal hydroxides, it is increases down the group. So we can add here that the solubility of metal hydroxides here we can add the solubility of metal hydroxides increases down the group, and all are good, I mean very strong base, and they are said to be alkali because all are water soluble, right? So CSOH maximum soluble, then RbOH, then KOH, then NaOH, and then LiOH. So LiOH is the least soluble, right? So at room temperature, CSOH, you can say the strongest alkali. The strongest alkali is CSOH. And solubility down the group increases. So this is all about hydroxide, peroxide, and oxide, superoxide, nitride, right? Now the next reaction is sulfide, reaction with sulfur, right? So all metal reacts with sulfur, reaction with sulfur, reaction with sulfur. So all metal reacts with sulfur to form the sulfide and polysulfide also. So all metals reacts with sulfur, and produces sulfides and polysulfides as well. Polysulfides, right? So metal plus sulfur, you will have M2S and M2SN. This is the polysulfide and this is sulfide, and N is equal to all elements form. And what is the value of N here? N is here 2, 3, 4, 5, 6, etc. Right? So see, sulfide is this. If this is 2, then this is S minus minus. And if it is S3, then S like this. If it is S4, then right. So these are the sulfides and polysulfides. So all the metals, no choice, all the metals reacts with sulfur and forms sulfide and polysulfides. Now see, indirect methods are also there. You can prepare these by indirect methods. Suppose that if you have taken Na2SO4, if you reduce this by reducing carbon, so if you take this sodium sulfate and reduce this with carbon, so you will have Na2S plus carbon monoxide, right? So 4C and 4CO. So reduction of sulfate also gave the sulfite. One more method you can use, acid-base reaction, you can use H2S. So you have hydrogen sulfide NaHS plus H2O and Na2S also, right? So NaHS plus H2S, so you will have Na2S plus H2. So these are some indirect methods which can be used to prepare metal sulfides of this reaction, right? So these are the sulfides. Now see, let's see halides, right, and polyhalides. So reaction with halogen, X2. So all metals reacts with halogens to form halides, right? So M plus X2 and all will form MX type halide. Right? So all form MX type halide. Okay, and polyhalides are also formed. So suppose that if you take Ki plus I2, right? So you will have Ki3, K plus I3 minus, right? Similarly, if you take KBr plus ICl interhalogen compounds if you take, then you have KBrICl, right? So these are the polyhalides which are formed by this group metals, right? So here if you take lithium, so which is the smallest size, if M is equal to lithium, so lithium plus, right? If M plus is lithium plus, then the salts of lithium are hydrated, right? So lithium salts, they easily hydrated. So trihydrated basically. So if you take LiX, so this is hydrated, right? And few salts of sodium are also hydrated. And bottom elements means potassium, rubidium, cesium, they hardly forms the hydrated salt. So in the first group, in this group, lithium and sodium salts are hydrated, and potassium, rubidium, cesium do not form hydrated salt, right? They do not form hydrated salt. Potassium, rubidium, cesium do not form hydrated salt. So this is very important point. Only you have lithium, due to the small size, it has tendency to form the hydrated salts, right? Now see, hydrides, all the elements reaction with hydrogen. So all these elements reacts with hydrogen and forms the salt-like hydride, MH, salt-like hydride, right? So it means all have this H minus, and with water they reacts with water and forms what? Hydrogen gas. Suppose that if you take LiH, so on reaction with water, this will produce LiOH plus hydrogen. So ionic character, what? So the ease with they form this, that is decreases down the group, and hydrides, they all the hydrides are ionic or salt like. Covalent character, basically in lithium hydride, covalent character more. As we move down the group, covalent character decreases, ionic character increases, right? So as you move down the group, the ionic character increases. Now see, some other complex metal hydrides are also known, and all they are very good reducing agent used in the organic reactions. For example, lithium hydride on reaction with AlCl3, this will produce LiAlH4. Lithium aluminum hydride, a very powerful and good reducing agent used in organic synthesis, right? So these are some complex metal hydrides, and they are also this LiAlH4 we can use for inorganic preparations as well. For example, if you take BCl3 and lithium aluminum hydride, the short form is LaH. So you have what? B2H6. Diborane you can prepare. If you take PCl3, so with lithium aluminum hydride, you have PH3, phosphine, right? And SiCl4 plus LaH this will give SiH4. So this easily reduce halides into corresponding hydrides. So these are the few reactions, reduction reactions. Reduction reaction of inorganic salts by lithium aluminum hydride. One more important compound we have for the organic reduction, that is sodium borohydride, that is prepared by this method, sodium hydride plus BOCH3 whole thrice and 230 to 270 degrees Celsius. So we will have NaBH4. This is also a reducing agent, right? Okay, 4NaOH. So this is also a good reducing agent, and this is also reducing agent. This is better reducing agent. This is and this is mild. So mild. So this is selective. Right? So sodium borohydride, this is a selective reducing agent compared to the lithium aluminum hydride, right?